So what we're going to be looking at today is our IR spectroscopy. Before we get into it, we need to do a little bit of summary because I was running a little bit slow with the lectures. So one of the things that you'll end up learning after you draw out a whole bunch of Lewis structures is that ultimately we don't really care about you drawing out and following all those individual steps. What we care about is that you can identify, in theory, self-identify these really important aspects. These important aspects are kind of summarized in this chart below. And so what I'm talking about here is that when we look at carbon, we see that there are a couple common bonding motifs, meaning that if carbon is to be neutral, it has to have 4 bonds. That does not mean, so be careful in this, that does not mean that that is 4 single bonds. Those could be a mixture of single, double, triple bonds. If carbon was going to be positive, it will have 3 bonds and that positive charge. If carbon was negative, it's going to have 3 bonds and that lone pair. We'd go through and do the same kind of reasoning behind nitrogen and oxygen. We don't look at our halogens or hydrogens. Any guesses why? Hopefully you could come to the conclusion from your Lewis structures that your halogens and hydrogen all can really only have 1 bond, which means we aren't going to be too concerned about charges. Hydrogen's octet is just 2 electrons, so the single bond satisfies it and we don't have to worry about it. The halogens will have that 1 bond and then 3 lone pairs, so 6 total electrons around the halogens. Hopefully you'll do enough practice so that you recognize all of these patterns. If you want to skip the practice, can't say I recommend that, but if you're going to skip it, you need to have this chart memorized. So everything we just discussed in those first 2 minutes here, nailed down, memorized, 100%. No questions asked. Next part of this that we haven't quite reached yet is how do we end up going about drawing these? When you look at typical Lewis structures, we specify all the bonds, we specify all the atoms, and that can get really redundant, particularly if we look at much larger organic structures. You think biochemistry if you really wanted to, DNA, RNA, proteins. Those are massive, massive structures. If we specified every single atom with its symbol, we'd get very, very tired. So we've kind of come up with a simplified method. Every point in chemistry is going to be specified as a carbon. So we don't need to write the C. It is assumed to be a carbon. So that's a nice little handy trick. Well, where is there a point? So let's clear everything off here. Look at a quick example. If I draw a line, how many points are on that line? Well, each end of that line is a point. So what I've specified so far by just drawing the line, let's go ahead and show the implied information in red. I've specified that I have 2 carbons. Well, that's a nice little bit. Just drawing a line, I've also specified these carbons. Well, rule number 2 is that hydrogens will be implied to carbon. And that's because the reactivity between our carbons and hydrogens are relatively small, because there's a difference in electronegativity that's very, very small. So you go back to that bond argument we were talking about. The bond between a carbon and a hydrogen is covalent. No polarity difference. We're probably looking at something relatively unreactive, which means if it's not going to react, who cares? Let's just hide it. So we end up hiding hydrogens. So we imply them around our carbons. And we'll do that in such a way that we satisfy the octet of carbon, or ultimately the bonding patterns which you've memorized for carbon. Well, how many bonds does carbon need to have? It needs to have 4 single bonds, or 4 bonds. We've only specified 1, so the rest must be hydrogens. So just by drawing 1 single line, I have now specified everything in red. It's become implied. So it can shorten a lot of the amount of work that we have to go through in drawing our structures. Other little bits and pieces that will keep popping up every so often. Charges will never, ever, ever be implied. Okay, you must show the charges. And it's ultimately because we've decided that we can imply hydrogens. We can't imply both hydrogens and charge, because if we, for instance, erased that positive charge on our carbon, Okay, if we look in that area, just draw your attention to it. How do we know that there's a hydrogen there or a positive charge? We really wouldn't know. Okay, so you have to absolutely make sure that you specify your charges. Don't cheat on that. You'll determine your charges through that formula charge calculation that we've also talked about when we talked about Lewis structures. Our last rule, our nitrogen, oxygen, and halogens will often have implied non-bonding electrons. So we won't imply hydrogens on our nitrogens and oxygens. We have to specify those. But we might very well imply the lone pairs, okay, those non-bonding electrons. I will try my best to never do that because it's very misleading and you could easily lose track of the chemistry. Okay? So if you're reading through the textbook, you'll probably see that they stop specifying the lone pairs. Make sure that when you draw them out, you draw in the lone pairs. Okay? So that's kind of the goal of your Lewis structures, trying to get those rules memorized or ingrained in your brain. The next part would be that we need to use structure and not formulas. Okay? And this slide is kind of summarizing this. Our formulas are way too vague. If we take a look at C3H8 or anything really smaller than that, it doesn't really matter what we end up doing with it. We will always end up with the exact same structure. Always results in that. There is no other option. Okay? So we could go through and draw the Lewis structure, or we could look at the simplified formula. And you'll notice that I also specified a condensed formula. We use the condensed formula to try and better represent the connectivity in our actual compound. Whereas if we just use the formula, we don't see that connectivity. When we jump up to 4 carbons, we do run into an issue. You'll notice that we've got the exact same formula for the next 2. But we end up with rather drastically different structures. And we also have slightly different versions of how we would go through and represent the condensed format. It really just takes a little bit of practice, getting used to being able to read and interpret these things. Be aware that the condensed format is something that will show up on tests. Probably one of my least favorite ways to represent structures, but it does show up, so you are going to be responsible for it. So you do need to practice that. If the sapling homework doesn't give you a whole lot, which in general it's not going to give you a lot, you might need to use the textbook to find some more examples. Okay? So, structure, important, avoid formulas, here on out. You ever give me a formula, I'm going to tell you it's wrong. So, at the end of chapter 3, what we start to do is connect these different structures together, and we start to evaluate something known as functional groups. And when we looked at organic chemistry, we really simplified things down to just a few different elements. We're dealing with carbon, hydrogen, oxygen, nitrogen, and our halogens. We can then look at how the size changes or the electronegativity changes to determine the reactivity of that individual atom or bonds around that atom. We could also go through and change how those atoms are connected to each other. So we could have single bonds between all of our atoms, or we could have double, or we could have triple bonds. If we change how the atoms are arranged, we're also going to change the reactivity. If the reactivity changes enough, we give it a new name. Think about everybody in the classroom. If we all looked the same, we could all call each other the exact same name. But since we all look slightly different, we use different names to help us distinguish between each other. We're not collective Borg. We're not V1 or 7 of 9 or whatever your numbers are. Simple functional groups. So we can now start to look at our individual types of functional groups. We could look at our single bonds, our double bonds, and our triple bonds. These are kind of our relative first pass. You are responsible for knowing the name and how it corresponds back to the structure. So start working on getting these nailed down. You will see questions on this both in the homework, and I will ask questions on it on the exam, which could range anywhere in difficulty from here's a structure, identify all the functional groups, or it could be as generic as give me the name and structure for 5 functional groups. So you need to be able to recall these names pretty quickly. When we talk about them in class, I ask you about a carbonyl, you need to be able to think immediately, carbonyl, carbon-oxygen double bond. Okay? So make sure you get those nailed down. You'll notice I said that these are just the simple functional groups. We can make them more advanced. by now stringing multiple functional groups near each other. When we take a look at the carbonyl, it's technically just the carbon and the oxygen. But what happens to the other bonds coming off that carbon? Carbon needs 4 bonds. So the carbonyl is a non-useful unit or a non-central piece. We need to add some other things to it. If we add a carbon and a hydrogen in those missing spots, we've got an aldehyde. If we add 2 carbons, we're looking at ketones. So again, as we substitute in different atoms, we potentially change the chemistry of our central functional group. That then requires the use of a different name. You are still responsible for these more complex functional groups. So just kind of be aware that as you move through the semester and both second semester, you're going to start looking at more and more functional groups and looking at more and more of their reactivities. And yet, again, even more possibilities. The amines and the hydroxys, or alcohols, can also get subcategorized into primary, secondary, or tertiary categories, as shown here. We will talk about these in more depth throughout the rest of the semester, but if you take a look at your alcohol, what we're looking at is how many carbons are attached to where our alcohol is located. Well, there's 2, secondary. If we take a look at our nitrogen, slightly different rule. Our nitrogen is our central reactivity. How many carbons are attached to it? Oh, 2. So our secondary means 2 carbons. What does our primary mean? Good guess. 1 carbon, and our tertiary, we're looking at 3 carbons. We can look at those 3 carbons around the carbon where our alcohol is located, or we look at the 3 carbons all directly attached to the nitrogen. Just kind of the rules. You'll notice that we don't use the exact same nomenclature system, and that's because if we take a look at the oxygen with 2 carbons bound to it, call that an ether. So it gets a slightly different name. Okay. Aromatic structure for some reason is not showing up, so we can draw that real quickly. What we're looking at with our aromatic is this system. We've got the formula C6H6. Remember all those implied hydrogens and carbons. Okay, so now that we've got an idea of all the structure, we now need to want to be able to figure out how we can identify what our structures are. Remember, these are all extremely tiny objects. We can't see them. So there's a variety of ways or techniques that we as clever little humans have come up with to try and identify what those structures are. So we'll be looking at the last 3 primarily, at least as far as the lecture goes, and at least the lab this semester. I'm going to try and incorporate some UV later on, but we're not going to see that this semester. In any case, our UV spectroscopy looks at electronic transitions. So we're looking at exciting an electron from a ground state to an excited state. Kind of a neat process. IR looks at causing our molecules to vibrate. Believe it or not, we can look at that vibration as something that's characteristic for an individual bond type. Mass spectroscopy, we aren't really using any energy here, we're actually just kind of destroying it. We blow our molecule up into billions of pieces, and then we look at the size of those pieces. Kind of a neat idea. And then NMR, probably the most useful of these, at least as far as I'm going to teach it, analyzes our individual atoms and how they respond to a magnetic field, an external magnetic field. So kind of a neat process. Almost all of these, or at least the 3 of them, our UV, our IR, and our NMR, are all relying on the electromagnetic spectrum. So no discussion on IR or any spectroscopy is going to be complete without at least including a slide like this. You've got the relationship between energy, Planck's constant, frequency, Planck's constant times speed of light over wavelength, all that kind of fun stuff in here. We look at our question. So this guy is wavelength. Hopefully this is all review. This one's frequency. We got Planck's constant. I think I spelled that right. And C is our speed of light. Okay. Hopefully you guys remember all of that from general chemistry. As far as organic goes, we aren't going to deal with that too much. You might see a question asking you to calculate or understand the relationship between energy and frequency, or energy and wavelength, but that's going to be fairly rare, few and far between. If we took a look at kind of the spectrum, as this figure from Pearson is so kind to let us use, if we look at increasing energy, so radio waves up to our gamma rays, we can divide up the electromagnetic spectrum into ultimately arbitrary sections. So that line between microwave and radio, kind of questionable. We just kind of decided that's where our difference is, so we put a line there. Same difference on each of those divisions. Very much the same way that we look at our bonding. Our covalent, polar covalent, and ionic are all kind of a spectrum. At one end of that spectrum is our ionic, at the other end is our covalent. Important things to recognize: our gamma rays are going to be our highest energy, which also means the highest frequency, but the lowest wavelength. Okay, so we get that kind of inverse relationship that, if you happen to remember this equation, is easily derivable by just kind of picking some numbers. Okay? Our radio waves look at nuclear spin transitions, NMR, nuclear magnetic resonance. We're taking our nuclei and putting them in a magnet and then hitting them with radio waves to see what happens. Raman spectroscopy is actually using microwave, which we won't deal with, so you don't have to worry too much about that. The one we're really concerned about is this molecular vibrations, and this is IR. And then our electronic transitions are ultraviolet visible spectroscopy. Okay, so that's kind of how we end up cutting up the electromagnetic spectrum to do what we want. Okay, so let's push it a little bit further. Within our IR region, we're usually specifying wavelengths as shown there. We can use centimeters or pretty much any distant unit we really wanted. For some reason, whenever dealing with IR spectroscopy, we tend to rely more on that centimeter unit, sort of centimeter unit. I forget the historical reasons behind it, but IR spectroscopy uses wave numbers, which is the inverse of the wavelength, to determine the actual ranges. So when we start reporting where we see signals, what we're talking about is 1 over our wavelength for that energy signal. It's not the frequency, because the frequency and wavelength are related through Planck's constant and the speed of light. So it's close to it, but it's not exactly the same. Okay? The typical range that we're looking at for our IR spectroscopy, so when we look at an actual spectrum, it will typically range from 4,000 inverse centimeters to 400 inverse centimeters. And you will be responsible for knowing parts of that. The big relationships that you'll see show up every so often will be this: as our energy increases, our frequency increases, our wavelength decreases, and our wave numbers increase. Remember, the wave numbers and our frequency are very, very related. Okay? A wave number is 1 over the wavelength. Our frequency is Planck's constant times the speed of light over our wavelength. So they're very, very closely related. One of the things that's nice about using this system is that if we increase the energy of our bond, we increase our wave numbers. So we've got some interpretive abilities there. So, IR spectroscopy. Really what it does is vibrate bonds. All bonds can be approximated as 2 weights on a spring. So we could pull one of those weights away from the other one, and when we let go, it goes through and does this oscillation. That oscillation is dependent on a variety of things, and we could look at that as a frequency, okay, or the wavelength of that oscillation. And that's really what our IR spectroscopy is. So we take an individual molecule with all of these little springs inside it, and then we fire IR light at it. If the IR light that we fire at it matches the energy of the bond starts to oscillate. So it absorbs that light. Well, then that means that that light doesn't make it back through our instrument, and we now see a signal. Okay? There's tons of different bond vibrations, so if you're going to look up at a table of IR information, you'll find that you can get all sorts of crazy stuff out of IR. It's a lot easier than that. We won't be going into a whole lot of them. What you'll really need are the bond stretches more than anything else. Okay? And there's an image, and if I was in class, I'd wave my arms around and give you an idea of what's happening with each of these diagrams. So then the next part is what happens if we change the weights on the spring, or if we change the spring itself. How does that end up changing our frequencies? Okay? So one of the smaller observations that you could make is if we went through and changed the weight on the spring, we end up changing the energy of the bond. Okay? The heavier that atom gets, or if we pick one, so if we take a look at our top three, we're saying we're starting with carbon, which we could pick as kind of our wall. What happens is we change the weight of the atom on our spring. Well, it turns out that our bond energy decreases. Okay, so we can see that as we shift, the energy slightly decreases, and at the same time, what happens to our frequency, or sorry, our wave numbers? Our wave numbers also go down. So kind of a neat observation. Probably will not see that in this class or even on the ACS test. If you push through to more advanced chemistries, you'll probably see something with IR potentially showing up. Okay? The more important one that will show up at very least at the very end of this is that our frequency is going to increase with increasing bond energy. So as we make a stronger bond, we see the frequency increase. So the big nice comparison here is if we take a look at moving from a triple to a double to a single, we end up seeing the energy of the bond change, and hence also the frequencies. So just kind of a neat thing to notice. So if you start to notice that a bond is going to get particularly weaker, you might expect that that signal is going to show up at a lower frequency. And yes, we will look at an example at the end of this, the very, very end of this. Subtle point to discuss. It shows up very, very rarely, but it is kind of important to mention. IR is really looking at kind of an electric field. So what we want to see is a dipole. So all of the signals that we detect are ultimately due to a dipole. And pretty much all bonds have dipoles, pretty much. Even when we look at a carbon and hydrogen, I know we said that that was a covalent bond, but the electronegativity is not exactly the same. Neither is the size. So we do end up seeing a slight dipole in this case, probably going this direction. So we see a slight dipole in that bond. If we then went through and changed it, say to an oxygen, our dipole gets even larger because the difference in electronegativity is a lot larger. Okay? The larger that dipole, the more intense the absorption that we see in IR. The smaller the dipole, the less intense it becomes. So most of the bonds that we'll see this semester, I might throw an exception in there just to throw a wrinkle into it so you can see what happens, have dipole moments. These dipole moments are then IR active bonds. Okay? However, there are some bonds that have no dipole moment. Even though that bond is present, it does not show up in the IR because of the lack of a dipole. One of those examples is a triple bond. If we went through and now made this completely symmetrical, there is no dipole moment in this molecule, which means we can't see that triple bond. Okay? So our triple bond is known as something in this case as IR inactive. That requires that it's symmetrical. If instead of having a hydrogen I put CH3, now it's not symmetrical, we do see the triple bond show up. Okay? So watch out for that symmetry issue. Really the only place it shows up is with your triple bonds, particularly your carbon-carbon triple bonds. Any other case, it's not that big of a deal. You'll see the bond show up in your IR. Okay? How do our instruments actually work? I'll leave you to kind of look at this in a little bit more detail if you're interested in it, but ultimately what we've got, at least in our old school fashion, is that we have our source of IR light. That IR light bounces through a reference cell. Okay, we need to be able to zero out whatever other junk might be in there. Remember, there's a whole bunch of air in here as well as over here. If there's something in there that's absorbing IR energy or IR light, that's not within our sample. We need to be able to cancel that out. So that's what the reference cell is there for. Determine what that reference signal is. I can then subtract that from my sample signal so that I get only what was in my sample. Okay, so a lot of spectroscopy will do this. We'll always have some kind of zero to compare things to or to remove stray data. The light then goes up and gets passed through a monochromator, which is ultimately what tells us the exact wavelength that or exact wave number that we're evaluating. That monochromator will then let only that wavelength of light pass through to the detector. The detector happens to have a tie back to the monochromator, so it knows when it's seeing light what that wave number is, and it can generate a plot. Okay, that old school process used to take a whole lot of time, massive equipment, kind of a big pain in the butt to deal with. Technology is advanced, and we end up using a new equipment known as FTIR. The FT stands for, hopefully none of you are that good at math and know how to spell that, Fourier transform. It's a mathematical simplification, I believe, so it will allow us to interpret the data, or the computer interprets the data for us and gets us to our spectrum much, much quicker. Okay, so we can get much faster scans. We can average our scans to get better data because we can take the scans much, much quicker. We can get more scans in there to be able to average, and we get cleaner data. It also allows for an internal calibration, and then one of the other big advantages is that we can now condense the entire IR unit into a much smaller package, so it doesn't take up half the room to actually run. Okay, so our Fourier transform IR spectras are what you will probably see if you were ever going to use an IR instrument, and we will be using one in our lab, and it is definitely an FTIR. So, what are the regions of the spectrum we could analyze? Depending on the professor you've got, you might very well see something like this. This is ultimately the old school method. This is what I grew up with and what I was trained on, but it's way, way overboard. You would never expect anybody to actually memorize this, and it's almost impossible to interpret, particularly in an exam situation. But just to give you a kind of an idea on it, you can see both at the top, I know that was a little bit difficult to highlight, and at the bottom, we're highlighting that 4,000 to 400 inverse centimeters. So that's our wave numbers. Along the side, what they're trying to show is they're classifying things according to individual functional groups. So for instance, if we take a look at the alkenes, because they're kind of hopefully a little bit easier for me to highlight, our alkenes are known to have signals wherever we see those solid lines. So those two solid lines correspond to ... If you zoom all the way in, you might be able to see this, a vinyl CH-CH2. Okay? So you would go through and try and interpret where you saw a signal and where does that match up. So it's a lot of back and forth. The real way is ultimately going to involve a lot of back and forth too, but this method was really, really tedious. So let's simplify this a little bit. To simplify, here's a real spectrum. You're going to be responsible for interpreting this spectrum. But if you take a look at this bottom section here, it says fingerprint region. The fingerprint region, much like our fingerprints, will characteristically identify a compound. But when you walked into the classroom, did you come up and ask to see my fingerprints to prove that I was the instructor for the course? Because, I mean, that's how you identify things, right? Through a fingerprint. Okay, we got other things. Okay? So when we're looking at IR spectroscopy, we tend to ignore the fingerprint region. Depending on your instructor, like at ASU, they have you cross it out. That's awful. Okay? There's tons of information there. We don't want to completely ignore it. We just want to be careful analyzing it. Okay? Typically, they say it ranges up to 1400. If you ever watched me, which you will watch, analyze IR spectra, I typically ignore everything in that 1600 and lower range. Okay? The only reason I'll go into that range is if I have some more information about what my compound is to see if that bond could potentially show up in that range. Okay? So until I have that information, I ignore that area. Along the lines of ignore all those little words. We don't care about that. Okay? So what we're going to be concerned about when we go through to evaluate our IR spectrum is ultimately the 1600 to 4000 range. Okay? That's where all of our primary functional groups will show up. That's where we need to look within an individual spectrum and evaluate what we see. Okay? And then interpret that based on what types of bonds those would be. Okay? This could be a really difficult process, except ultimately what you just need to do is match. Does this signal, okay, let's say these peaks here, what does that look like if I go back to, say, that previous table? Okay, and this is where it gets rough. You'd go through and say, okay, where did that signal show up? Well, it shows up about 3000. So I would look in my 3000 range. Whoops, sorry. I would look in my 3000 range right in here, and I'd say, okay, anything with a line there could potentially be that functional group. So it's probably not an ether, because ethers don't show up. Probably not a ketone or an aldehyde, because they also don't have signals there. Okay? We can do a little bit better than that. That's why I don't like this chart. So what you really want to do is not just compare the frequency, but what the signal looks like. And that previous chart didn't do that. So if you take a look at the file, if you look at your modules, or the module, or if you go to modules on the Canvas site, I've linked in, first off, the link to this video, so hopefully you found it that way. I've also provided a link to my spectroscopy background information, which gives a lot of the general information that's shown in this, as well as the next important, oh man, sorry, I skipped a little bit, the next important part, which is looking at what each of these signals look like. Okay? So before we even get into what they look like, let's evaluate the sections that I think are going to be critical for you to memorize. So on this slide, we've got individual bond types listed on the left, so we know what bonds we've got to work with. We've got the wave numbers. That's a W, by the way. I know that looks a little confusing. Our wave numbers, and then we have some description of the signal. Okay? Words are pretty awful. Pictures worth 1,000 words, so we'll look at some pictures a little bit later. These absolutely memorize. No questions asked. Nail these down perfectly. Won't take that long. It'll go pretty quickly, particularly after you do some practice with these. You'll pretty much have these nailed down anyway. If you want to prove how really awesome you are, then memorize these as well. Okay? If you really want to go crazy, then you can go all the way back to this guy and memorize all of that. Please don't. That's way more work than you should ever want to do. Okay? But if you memorize the rest of these that are on my BA list, then you'd be pretty solid when it comes to IR, and you could probably get away with solving almost anything I throw at you with just the IR without having to deal with other stuff. So it is going to be kind of helpful to go through and spend that time. Nearly all of those are listed off then with these individual images. So our alcohols, for instance, were listed previously as a broad intense peak at 3200 to 3500. Well, what that means is this signal. This, by the way, that we might consider a valley, is our peak. Okay? So what we've got here is a broad intense peak. We can look at the numbers depending on the source. It tells us that's 3317. That falls right in between our 32 to 3500 range. We're looking at an alcohol. If we take a look at the amines, again, we could go through and evaluate the description in words. Not easy to go through and pick out, but maybe if we take a look at the image, we can see a little bit more cleanly what's going on. I will note that the amines are very tricky in the respect that sometimes you'll see them as sharp, sometimes you'll see them as broad. They will never, ever, ever be as broad as the OH. Your alcohols are always a much broader peak. Just be aware of that. Other things that we can look at are CH bonds, show up a little bit lower, usually right about that 3000 range. The big one that I would recommend that you memorize would be what I've got classified as our A and B here. Our alkenes, where we have a carbon-hydrogen bound to an sp2 carbon, show up just above 3000. So if you drop a line on this 3000 and go up, anything on this side is an sp2. Anything on this side is an sp3. Okay? So can be helpful. If we have just sp3 carbon hydrogens, then we're looking at an alkane for a functional group. If we're looking at an sp2, we're looking at alkene. Okay? The last one for our CHs is our aldehydes. That was on that BA list, so I'll leave you to kind of interpret that on your own free time. We then have our carbonyl. Okay, that's the next really, really big one. So as far as really memorization, we've got our OH, our NH, carbon hydrogen sp2 and sp3, and our carbonyls. So if I did my counting right, I've got 5 things that are critical to have memorized. The carbon-oxygen double bond is again a very, very obvious signal. Shows up centered right about 1700. It has some fluctuation, which we'll look at with our conjugation effects here. And it's a super intense peak. Okay, so we got an example there. What happens with the conjugation? Okay, so this goes back to what we ended our last lecture on, resonance. Okay, if we take a look at the structure on our right, we have the option to do resonance. And what we can do is draw an alternate version of this structure. And that alternate version looks something along these lines. No, it's not as nice as the first one drawn because we have the charges in there. But this resonance can help us start to consider where we might expect to see the signal for our carbon-oxygen double bond. Okay, well how? Well, carbon-oxygen double bond, in both cases we'd expect them to show up around 1700. Okay, the one on the left, strictly 1700. We aren't going to see a lot of variation off of that. But how about the one on the right? When we look at resonance, what we're saying is that neither one of these structures is perfect. We have to look at them both. Okay? They're both part of the picture. So if we average them out, do we have a full-on carbon-oxygen double bond? In one case, yes, we do. In the other case, no, we don't. So we're somewhere less than a double bond. So one of the things that we could go through and do if we had memorized that BA list is figure out where a carbon-oxygen single bond was. Turns out it shows up at a lower frequency. So for this carbon-oxygen double bond, I would expect something lower than 1700. So I would expect to see that carbon-oxygen signal, that big intense signal, but it should show up on the lower end, probably closer to that 1650 range, because that carbon-oxygen double bond is not truly a double bond. It's partially a single bond. The other way we could evaluate it, way back in those few slides, we looked at what happens when we change the strength of the spring. Well, we went from a double bond to a single bond. We weakened the spring. If the spring gets weaker, what happens to our wave numbers? Again, they get smaller. Okay? So resonance can have a pretty huge effect on where your overall signals show up. Okay? I really did want this to be just 30 minutes, so I'm going to move on from there, and we'll look at a couple quick examples. Please feel free to pause, and I'll go ahead and repeat pause for each of these, and then I'll go through and describe what I see in each of these spectra. Okay, so let's go ahead and say pause. 1, 2, 3. What I see. Real quickly, I draw in, man, I'm not very good at drawing a straight line. Okay, my line shows that this peak is greater than, that is an sp2 carbon-hydrogen stretch. This peak is just to the right of it, that is a carbon-hydrogen sp3. Very quick and easy labeling that. I see another sequence of peaks in here. And yes, it can be very tempting to go through and label those. But remember, this should be very superficial. If you go back and look at the example peaks, for the CHSP3s, there's usually 3 or 4 of them. Okay, so don't get peak happy or peak label happy. Go for kind of a bulk image and then hope for the best from there. Now it can get a bit tricky. This signal right here, this signal right here, really intense, but it shows up at 1600. Okay? Having some experience with this, I might take a stab at it and say that I'm probably looking at a carbon-carbon double bond with the presence of this extra signal that's showing up probably about 1475. Yes, I am roughly guessing. I would go through and say that those are an aromatic. Okay? Based on your experience right now, I wouldn't touch it. Okay? What you should be seeing out of this is only the CHSP2 and the CHSP3. Unless you are given more information about what that structure might have in it, the aromatic identification is way above and beyond what you guys need. The rest of those signals fall well within the fingerprint region. Again, wouldn't worry about them until I had more information. Okay, so next spectrum, and I will go ahead and pause. 1, 2, 3. Again, quick evaluation. I see a big broad signal looking at an OH. Drop my 3000 line. These peaks are all to the lower end of that. I'm looking at a CHSP3. I look further to the right. The next big signal I see was at 1475 at best. That is definitely under my 1600 range. I'd leave it alone. I wouldn't analyze it until I had some more information about the structure. So again, we see this spectrum with a whole bunch of different signals, and the only thing I really evaluated was 2 sets. Okay? We even have a signal up in here. Very weak though. Nothing on my list suggests something weak in that 1700 range. If anything's going to be there, it's going to be that carbonyl real strong. Okay? So again, keep it simple, keep it quick. And then last one before I go ahead and let you go. Pause. 1, 2, 3. And I will real quickly go through this one. Here's my 3000 line. CH, hopefully at this point you now recognize. SP3. Counted out at 1617. This peak is roughly at 1700. I'm looking at a carbonyl, carbon-oxygen double bond. Rest of that is fingerprint region. I won't evaluate. Here's where we're going to run into a big old hiccup, okay, particularly as you practice these more. This peak, okay, definitely not an OH, vaguely looks reminiscent of an NH. Okay, the reason why it's vaguely and not really an NH, if you go back and look at the NH rules, NH says 1 peak or 2 peaks. If you look at that spectra really carefully, there are 3 peaks there. Okay, that is not an NH. The next part about it that makes it even trickier as to what it actually is, it's showing up about 3400. Half of 3400 is 1700. At 1700 we have a wicked intense peak. What we're seeing out here is something known as an overtone. It's a signal doubling. The carbonyl peak is sometimes so wickedly polar and intense that the signal doubles, and we end up seeing a signal showing up at roughly double that wave number. And it does tend to carry the same kind of patterning. You usually see a fairly sharp peak and then a couple bumps coming after it. And that's exactly what we see here. Whether or not you're right ultimately comes down to what spectra you've got to work with. Okay? Like I said, it's really going to come down to practice. Go ahead and download that IR activity. Go through and start working some of those problems. It's going to require you labeling multiple things back and forth. Use the spectra packet. Use the guidelines that are outlined a little bit earlier here. Okay? I went through and put them each on individual slides. Use these kind of images to kind of match up what things you see, or really, unfortunately, what things you think you see until you're comfortable identifying them. Okay? Takes a little bit of practice. Hopefully that IR activity is within your grasp after this. If you got any questions, feel free to post to the discussion board or send me an email, and I'll try and help you out as best I can, either over the weekend or maybe even in class on Wednesday when we meet next. Okay? Have a good weekend.